So a quick recap. I stated the goal of our sampling is to find out information about a population parameter. And of course, it helps you to remember the difference between a statistic and a parameter. A statistic is a numerical characteristic of a sample, while a numerical characteristic of a population is your parameter. So you want to keep those things straight. Here's our notation for those things. Sample mean, denoted by x bar, estimates the population mean, denoted by u, s and sigma, p hat and p respectively. Now the big thing we did last week, and I'll reiterate it here, was we looked at different distributions. And we started out with 3 distributions and sampled from them and calculated the distribution of a sample mean for various sample sizes. So if you start out with a normal distribution, the sample mean is always going to continue to be normally distributed. So all of these are normal distributions. But these two are clearly not normal distributions. If you started out with something here, then, well, this isn't a normal distribution, nor is this. That's for samples of size 2. But when you get up to samples of size 10, that's looking more normal, and so is that. And by the time you get to samples of size 30, your sample mean is going to have a distribution which is approximately normal. So there's 2 ways that the sample mean can have an approximate normal distribution, or normal distribution. And those 2 ways are either that you start out with a normal distribution, or you take a large enough sample size. 1 or 2. Now, assuming that your population mean is mu and standard deviation is sigma, for a large enough sample size, x bar, your population or your sample mean is going to have an approximate normal distribution. With this mean, which matches this, and the standard deviation, which is sigma over the square root of n. Likewise over here, if you started out with a normal distribution, it's going to have the same mean that you started out with, mu, and standard deviation is going to become sigma over the square root of n. So one way or another, x bar is going to have a normal distribution as long as your sample size is large enough. Okay, let's apply that to some problems. And I'm actually going to pull out a physical copy of the book, which is unique here for us. Usually we don't do this. And we're going to look at a couple problems here. These are very typical of the kinds of problems that I will ask you on an exam. So it says, use the central limit theorem. And exercises 5 through 7 assume that women have pulse rates which are normally distributed with a mean of 74 beats and a standard deviation of 12.5 beats. So we're going to write down this information and then use it to answer questions here for problem number 6. If one adult female is randomly selected, find the probability that her pulse rate is greater than 70 beats per minute. You might want to open up a Google Sheet here. And then if 25 adult females are randomly selected, find the probability that they have a pulse rate with a mean greater than 70 beats per minute. So, all right, let's take a look at that, see what we can do. I'm first going to start by writing down the information that the problem started out with. That women have pulse rates with a mean of 74 and a standard deviation of 12.5. So we'll call this example A, part 1. X is distributed normally with a mean of 74 and a standard deviation of 12.5. The first part is asking to find the probability that some value from this distribution is greater than 70. What are the chances of that? Well, let's start by drawing this. And So here's this distribution. What should I put here for the value at this line? 74. Awesome, thanks. Now 70 is going to be to the left of that someplace. And the only thing I'm really concerned about is I draw it to the left. So let's draw on a little line here. Which way should I shade? To the right of 70 or to the left of 70?
Right.
I got mixed signals on that one.
Right.
To the right. Yeah, thank you. So I want to shade everything here. That's the area that I eventually want to find when I do this. Okay. Well, what command is going to help me out with that if I'm doing this on Google Sheets?
1 minus norm dist.
Yeah, excellent. Well done. So we want to use norm distribution. Now keep in mind when I type in norm distribution with 70, it's going to give me the area to the left, right? That's not what I want. So yes, we're going to have to do 1 minus. So that much is going to be norm distribution. Remember, you have to type in the equals as well. Equals norm distribution of 70, comma 74, comma 12.5, comma what?
True.
True. Yes, well done. Awesome. The break hasn't like seen too much of a cognitive decline. Well done. Let's take a look at that. A lot of times I do this in 2 parts just because I like to be able to show you what's going on. Let me open up a new sheet here. So we'll do example A. So it's going to equal norm distribution of 70, comma 74, comma 12.5, comma true. And then I want 1 minus that. So I'll do equals 1 minus, and bam. This is a lot easier than what we used to have to do. You used to have to create a z-value for this and then look that z-value up in the probability tables at the back of the book. Wow, no thanks. I'm not nostalgic for the bad old days. Now, that much was what, 0.377 something or 0.3744. And then this part is going to be 1 minus norm distribution of all that. 70, 74, 12.5, and true. And that's 0.6255. Nice. So often, not always, but often there's 2 parts to these problems. The first part's going to have you do something with the distribution. The second part is going to ask you to work with the distribution of the sample mean. So let's take a look at the second part. Are we good with the first part? Did everyone able to get that number? Yes, no? Greg? No? Jackson? Good? All right. So let's take a look at part B. If 25 adult females are selected, find the probability that they have pulse rates with a mean greater than 25. So a couple things to take note of here. 1, we got 25. And 2, we're dealing with the distribution of the sample mean. What's the chance that their average pulse rate is more than 70? That's a different problem. They're not talking about just 1, they're talking about 25. So let's see what that's going to look like. I want the probability that X bar for samples of size 25 is greater than 70. Now, as far as your problem is concerned, when it comes to testing, this is where you earn the points. Typically, this is going to be a 10 or 11 point problem. 4 points for the first part, 6 or 7 for the second part. So I mentioned that to try and get your attention here, because this is the important part. Yeah, go ahead. Yeah. No, trying to find the orange shaded area, because we want to find the probability that x is greater than 70. That's going to be that area right there. Yeah. Now, the reason we had to subtract from 1 is because the way Google Sheets works. Google Sheets gives you this area. So that was 0.377 or 3744. And when you subtract it from 1, you get this. All right. Here's the thing. X bar has a different distribution. X bar for samples of size 25. Well, because it comes from a normal distribution to begin with, then it's going to continue to have a normal distribution. So it's going to be distributed normally. Now we're sampling from this right here. That's our parent population. Nothing to do with me. What's the mean of this new distribution going to be? 74. Same as the mean of your old distribution. That's cool. That means X bar is an unbiased estimator. How about the standard deviation?
Different.
Not quite 12.5.
Right.
Divided by the square root of 25. Divided by the square root of the sample size. That's the key thing here, is that by taking an average, you're less likely to get the extremes. It's shrinking your standard deviation. So we're going to repeat our calculation with this new distribution. So let me draw that. That's a good one. Usually mine are far from symmetric. Let's see. Still want 70, 74. And Google Sheets is still going to give us this area here, whereas we want the area to the right of it, which I'll shade in orange. This is the area that we're looking for. Basically, it's the same calculation that we just did. It's just that this time we've got a different standard deviation. So let's go back and look at that. So this is part 1. And let's do part 2. Some people will call it laziness. I call it economy of movement. I'm just going to copy this and paste it here, but I've got to make a change. What's the change I got to make? Standard deviation. Now here's the easy way to do the change. Even though I can divide by 5 in my head, let's just make Google Sheets do it. Just hit divide by SQRT of 25. Or you can divide by 5, or you can just say, oh, 12.5 divided by 5 is 2.5. All of them are going to give you the same thing. But you've got to change the standard deviation in the second part of this calculation. So what happens? The area to the left shrunk, the area to the right is going to increase. So there's your answer for part B. So that part gave me 0.0547, call it 0548. Norm distribution of 70, 74, 12.5 divided by the square root of 25, and true. So that's what your calculation should look like. And then 1 minus all that is going to give me, yeah, 0.945. Thank you. 0548 equals 0.9452. Yay. Beautiful. Beautiful. So 2 parts to these types of problems, generally speaking. They're not always that way, but generally speaking, that's what they're going to look like. How's that one looking? Thumbs up? Thumbs up? We're gonna do some more. We're gonna do some more. But if you have a specific question, fire away. Nothing specific? Okay. All right. Anyone else? Zoomers? Thumbs up? All right. Thank you. Let's try another one. Okay. Let's work with the manhole covers. And I admire the author for digging out stuff like this. I don't think I'd know where to find something like this. So according to the website torchmate.com, yeah, I surf there a lot, manhole covers must be a minimum of 22 inches in diameter, but can be as much as 60 inches in diameter. Assume that a manhole is constructed to have a circular opening with a diameter of 22 inches. Men have shoulder breasts that are normally distributed with a mean of 18.2 and a standard deviation of 1. Let's highlight those things. I want to come back to that. Normally distributed with a mean of 18.2 and a standard deviation of 1. What percentage of men will fit into a manhole? All right, probably going to be pretty high percentage. Let's write down a couple things and get ourselves busy doing some calculations. So this will be example B. This is part 1. X is normally distributed with a mean of 18.2 and a standard deviation of 1. Let's draw our distribution here, there. What shall I label my center line with? 18.2. How big were manhole covers, did they say?
22 inches.
22 inches. So let's draw ourselves, 22 down here. Now, if somebody's going to fit in a manhole cover, does that mean their shoulder breadth is less than 22 or more than 22? Less than. So that means basically I want this area to the left. So that's what I need. Unfortunately for us, that's what Google Sheets gives us exactly, is the area in the left tail. So we don't have to worry about subtracting from 1 in this case. All right. So for this first part, the 4-point part of the problem, that's going to be equals norm distribution of 22, and then the mean, which is 18.2, and the standard deviation, which is 1. What always follows that for this command?
True.
True. Nice. And that should be almost everybody.
These are technically in detail, yeah? I guess it's gonna be, yeah.
Yeah. Yep. So let's go over here and we'll write this down. Example B, part 1. So equals norm distribution. And once you see that it recognizes your command, hit the enter key and let it finish it out for you. That way you don't accidentally type in, a misspelling or something like that. 22, 18.2, 1, true. Is there a good chance that somebody's going to fit in there? Yeah. Yeah, you could bet the farm on it. There's less than a 1 in 10,000 chance that somebody wouldn't fit. So that's looking pretty good. So 0.9999. 9999. Nice. But part B here, the second part of this is going to be a little bit different than the first example we did like this. So the first example, that's very classic. That's typically the way they ask the problems here. But here for us in this problem, they make a little bit of a change. So let's see if we can't see what that change is. Assume that Connecticut's Eversource Company employs 36 men who work in manholes. If 36 men are randomly selected, what's the probability that their mean shoulder breadth is less than 18.5? Does this suggest that money can be saved by making smaller manholes with a diameter of 18.5? Why or why not? Well, let's find the probability first. The big thing to notice here is that we're talking about, where is it? Talking about the mean shoulder width being less than 18.5. That's for the 36 men that we're averaging. What's the chance that they have a mean or average shoulder width less than 18.5? Focusing on the fact that we're talking about a mean here. So we're no longer talking about X, we're taking something from this distribution. We're talking about X bar for samples of size 36. There's three aspects of how this is going to be distributed. What's the first part of it? Yep, it's going to be normal. It's going to be normally distributed. Keep going, somebody else. What about the mean? The mean is going to be 18.2. And here's where all the money is. Grace, want to give that one? What's the standard deviation going to be?
1 over the square root of 36.
Beautiful. 1 over the square root of 36. I'll go back and explain why later, but the author always seems to be choosing things that are a nice, easy square root. That's okay. All right. We don't have to worry about that as much as we used to. It's not as big of a problem for us. But the other part of this is we're no longer worried about the probability of being less than 22.2. They've changed things up. We'll find the probability that these 36 men have an average shoulder breadth that's less than 18.5. So that's a little different than our first one where they kept this number the same for both parts of the problem. That's okay. Not a big deal. Let's draw ourselves a little distribution here. Now I did kind of roughly try and draw it a little taller because the standard deviation is going to go down. It's not as spread out as it was. All right, I didn't do a great job, but that is as it is maybe. This time I want to find the probability that we're less than 18.5. So basically, can the company save money by building manhole covers that aren't as wide? It's like, oh, well, we don't really need that, do we? Well, maybe yes, maybe no. I still want the area in the left tail. So that's going to be this area here. Area in the left tail is going to be convenient because that's the way Google Sheets works, is it gives you the area in the left tail. Okay. I want that area. What's our Google Sheet command going to look like to find that area?
Norm is 18.5, probably 18.2, the square root of 36.
Perfect. Norm distribution of our x, which is 18.5, 18.2, which is our mean. Our standard deviation is no longer 1, it's 1 divided by square root of 36. Of course, square root of 36 is just 6, so if you want to put 1/6, that's fine. And then true. You're always going to use true for the norm dist command. Now, kind of like the last one, I'm going to borrow my calculation from part A to do part B. So this time there's two changes I got to make. First of all, that's 18.5. And secondly, this is going to be 1 divided by the square root of 36. Now, square root of 36 is just 6. So if you just want to do 1 divided by 6, that's fine. But there's your command. So is there a good chance that on average those 36 men are going to have shoulder breadths that would fit in an 18.5-inch manhole cover?
Yeah.
Nice. Yes, I agree. So this probability is 0.964, 06, etc. So about 0.9641. So okay. Yeah, please. That's a great question. Ironically, I got asked that in my morning class, and it's a great question. When you're dealing with a continuous distribution, it doesn't matter if I wrote less than or equal to. I could write probability that x bar sub 36 is less than or equal to 18.5, and it's still going to be the same. And the fancy reason for that is because the area underneath 1 point is 0. So that if I said, okay, well, we want the probability up to but not including 18.5, well, you can include 18.5 because the area underneath that last little bit is 0. So you're not changing those probabilities. That's different if this was a discrete distribution. If this was something like the binomial distribution, you're counting the number of pennies or number of heads you get in 10 flips, then the probability that x is less than 3, the probability that x is less than or equal to 3 are going to be different. Because one's including the 3, one's not. And that extra bit will make a difference. But here it doesn't. So great question. I'm glad you asked that. It doesn't make a difference to do less than or less than or equal to with a continuous distribution. Okay. Let's go back to the question that they ask when they're all done here. That's kind of like our part C. Does the result suggest that money can be saved by making smaller manhole covers with a diameter of 18.5 inches? Why or why not? I mean, the probability for part B was, 96, but is that the relevant probability?
Not the relevant. I think the relevant probability is it compares to the 99% in my opinion.
Good.
Because it's
Why?
always, because if you compare the two, there's really not a whole lot of difference. I mean, sure, you would in theory save money, but it would cost way more to replace everything than what you would gain in the end.
Okay. Does anyone else have a good different spin on that? Let's think about who's going down the manhole. Are you putting one person at a time, or are you taking 36 guys and somehow magically averaging them and taking their average and putting it down the manhole cover? Which one's more realistically the case? One person or the average? One person. Yeah, it's going to be one person at a time that's going down the manhole cover. So, it's great that you can work with the average and find out things about the average, but the average is not the relevant probability here. The average just doesn't really come into play when we're doing that part of the calculation. All right, so out of curiosity, if you really wanted to see, could you save money by making manhole covers with a diameter of 18.5, what you could do is take this probability here, let me copy it over here, and let me put in 18.5 here. So this would be the probability that one person has shoulder breadths that are small enough to get into an 18.5-inch diameter manhole cover. So what do you think of that probability? Is that good enough, or are you going to tell you're going to tell 38% of your workforce, nah, you can't do any work today? I don't know. That'd be a lot of people that wouldn't be able to actually fit in a manhole cover if you reduced it to an 18.5-inch diameter. So, yeah, the relevant probability is in part A, or first part. Have I talked to this class about the ridges on quarters?
Oh yeah, it's about
Yes?
how people used to shave.
Yeah, they used to shave them. And it was Isaac Newton that first put ridges on quarters. And the reason I mention that is because it's coming up here with vending machines. So somebody has to think about this stuff. And let's take a look what's going on here. Vending machines. Quarters are now manufactured so they have a mean weight of 5.670 grams and a standard deviation of 0.62 grams. So let's kind of highlight that information right now. A mean of 5.670 and a standard deviation of 0.62. That's some information we're going to write down. And their weights are normally distributed. All right, that's even better. A vending machine is configured to accept only quarters with weights between 5.50 grams or 5.50 grams, 5.550 grams and 5.790 grams. If one randomly selected quarter is inserted in the vending machine, what's the probability that it will be accepted? Okay, let's write down a few things here. Or at least I'm going to. Maybe you're ahead of me on this one. So this is example C. X is distributed normally with a mean of 5.60670 and standard deviation of 0.062. Oh, I know why. I moved that up. There we go. Let's draw our distribution. Now on your exams, I typically will give you blank distributions and you can fill them in as needed. I would suggest you do that. It helps you with your intuition. It helps you kind of double check. Are you drawing the right area? Are you thinking the right area? Does your answer make sense? I strongly suggest you do that. So for part one here, this is 5.670. We want to find the probability that the machine accepts a quarter. It accepts quarters as long as you're between 5.550 is less than X is less than 5.790. So that's basically the area between those 2 points. So let me draw them here, 5.79 and 5.55. You're going to have to do a little bit of work here. A little extra work that we didn't have to do in our first two problems. I want this area that's between these. So like I said, that's going to require a little bit more thought. The second part of it is to find the probability that you get an area or you get a coin or the average of 4 coins accepted into the machine with those same criteria. So if 4 randomly selected quarters are inserted in the vending machine, what's the probability that their mean weight is between 5.50 and 5.790 grams? Okay. So let me draw kind of our part 2 of this problem. That's going to be X bar for samples of size 4, and you're going to have to fill in that distribution. What's its mean? What's its standard deviation? Now I'll give you a hint. You should be looking at this distribution right here when you come up with the distribution of the sample mean for samples of size 4. We're still going to want the probability calculation kind of modeled in the above problem. I want the area between 5.55 and 5.79. I'm being lazy and not putting in the 0 here, 5.67. But I want that area. When you turn to Google Sheets to do this calculation, it's going to be a little bit more challenging. You're going to have to think a little bit how to get the area to the left of this, but not including this. So give that a shot. I will walk around, see how you guys are doing. If you need some help, please reach out. If you're watching this sometime later, then fast forward until I get rid of the pause button. So find these probabilities from Google Sheets. Give you a hint, there's going to be a couple different things you're going to do in your calculation. Distribution, you kind of blended that with implementation. It's okay. As long as you know what you're doing, that's okay. Yeah, if you just were. Well, since you're dealing with sample size 4, so you apply the standard deviation by the square root of 4.
Okay.
Okay, and then what are you going to do to finish up? Yeah. Mm-hmm.
First part.
Yeah. Gotcha. Equals. And then click that one. Minus and then click the other. I'm afraid so. Yeah, great. Alright. It's all right, no, it's all right. 0.947 and 0.9998. Oh, you gotta subtract 2.
Yeah.
You gotta
Okay,
subtract 2
so
from.
subtract this.
So you're gonna find the area to the left of this
Yeah.
minus the area to the left of that. That should be about 0.947.
Yeah, 947, right?
Mm-hmm. And then you gotta do it again down here for that difference distribution.
Okay.
But because this is a sample instead of
When you go for this area, you need to first find the area to the left of this and subtract out the area to the left of that. And that'll leave you the area between. So the norm distribution is this one minus norm distribution. That's the first one.
The person that was figuring out.
That's what I was.
Yeah, this one.
Okay.
They give you this. They give you the standard
the
deviation.
negative
think that's
values is the real and the norm
I'm afraid those are both right.
Negative.
So it's this minus this.
With
That's what you compare.
with the square root.
That's the second part.
And then
Okay.
So the second part, the difference is the distribution of all regular distribution. This standard deviation, 0.062 divided by the square root of the sample size. So you can use the same commands, but you gotta change the standard deviation. The standard deviation is no longer 0.062. It's 0.062 divided by the square root of 4. So copy those and just edit it would be my suggestion. Try it on the phone if you want, but. Sorry. Yes.
So it's probably, so it'd be,
I don't know.
it's like when it says
maybe you would.
for
Well, you could probably.
that's
I'm not looking into my computer.
if you know the function,
She's a computer.
know the formula of it, x bar minus b.
Odd.
I just don't have the block. I don't, George my I just didn't really.
If you put it through the USB, it'll work.
Yeah, it's just the computer's off, because it's dead and it's charging.
What's it say? It should say true.
And by plugging that into my computer.
See if this works, so.
Sure this is true. Oh, well. Safe on safe. More shots.
Yes.
Yeah. You seem distressed by that.
You do it? No, oh no.
So the standard deviation, the first part is given to you. So it's the 0.062, that's just how we're doing it.
Oh, it's, I see.
The second part,
Oh.
right, the sample mean, it's always that distribution divided by this, because that standard deviation divided by the sample size. Yeah, but I don't know, sample size.
Well, you too. So you can just copy and paste.
Copy them back here.
Just copy and paste from the
0.947, 0.99, or something like that.
Give me a sec, actually. Because I need to delete something. I need to delete the screen. this is for the first one.
I
You
mean,
have your
Okay.
values, right?
okay.
And then second you get this. And then let's do
All right, let's finish this one up, and maybe I'll make a couple summation remarks.
practice.
So in order to get this probability, you have to work a little bit harder than the previous problems, right? Because you've got to find the area between these two. We're going to subtract those two areas. So let's see what that's going to look like. It's going to be norm distribution of 5.79, comma 5.67, comma 0.062, comma true, minus the area to the left of this, which is going to be your norm distribution of 5.55, comma 5.67, comma 0.062, comma true again. And that should give you about 0.947 something. Is that right? Is that what you get?
Yeah.
Yeah.
Give me one more digit. 0.947 what?
1.
71. All right, nice. Now you're going to get the same kind of thing when you come down here for this calculation. The mean's going to be the same, 5.67. What's the standard deviation going to be? What's that going to change to?
0.062 divided by square root of 4.
Awesome, thank you. 0.062 divided by the square root of 4. You can just divide by 2, or you can type in 0.031, etc. But we're going to do the same kind of calculation again, just with that new distribution. So let me bang out both of those. So this is example C. So part 1, that was norm distribution of 5.55, comma 5.67, comma 0.062, comma true, minus, and it'd help if I could spell true, minus, and I'm going to cheat a little bit. I'm just going to copy this all over again and change that. Actually, you know what? I think I got it backwards. This should be 5.79. I want to do the rightmost one minus the leftmost one. So there it is, all in one step. And there you go, 0.9471. For the second part, so part 2, you can just kind of copy what you did here, paste it over here, but you got to go through and adjust the standard deviation. So I'm going to divide by the square root of 4, and divided by the square root of 4 is the same thing as dividing by 2, so I can do either one, whatever works for me. There's my rather long command, but this time I should get just about everything, about 99.9%, 99%, so nice. How many of you got that one? Question first, Ivy?
Where did the square root of 4 come from?
Square root of 4 comes from the sample size. So for the second part of this problem, you're looking at the mean weight of 4 quarters.
Oh, okay, that makes sense.
So that's where the 4 is coming in from, and that's what puts the square root of 4 in the denominator. All right, so some feedback from you. How many people got both parts right? All right, pretty good. Those of you who didn't, did you see what you did wrong, or can you correct your mistake?
Can you show the command?
Yeah.
Yeah, sure. Now, you don't have to do it exactly like I did it. You can do it in 2 parts. So if you wanted to do it in 2 parts, then you could do it like this. Actually, let me grab this one. So if you want to do it in 2 parts, oops, no, don't do that. Whatever. Error, undo, Command Z, use it all the time. So, no, that's not what I wanted. There. So for the first one, I want to make that 0.79. Second one, I want to make that 5.55. And then you got to subtract them. So you could do equals this one minus this one. Bam. And for the second part of this calculation, if you do it this way, it makes it pretty easy to do the second part of the calculation. Just paste it in here, and you got to change two things. Divide by 2, and divide by 2, or the square root of 4, whatever works for you. 4. And there you go. Same answers. So, is that helping? Looking good? Cam? Michal?
Can you still show us the above?
This one? So again, you can divide by the square root of 4, or you can divide by 2, or you can just type in, 0.062 divided by 2 is 0.031. All of those will give you the same thing. Cam, question on that?
Oh, I got it right the first time.
Okay. Ethan, looking good?
Yep.
Okay. Anyone else? Now, you might notice that the author tends to want to use numbers that have a nice square root, like square root of 4, square root of 36, square root of 25. Those are nice considerations. The reason the author does that is because the way you used to have to do it when I taught this class back in 19 Mumble Mumble was you would have to calculate a z-score. Now, let's see who was paying attention to the start of things. Chloe?
The formula for z-score,
Yeah, go ahead.
x bar minus mu, I think,
Divided by
divided by standard deviation.
sigma. Yes, that's nice. Now that's for a population. Now in spirit, it's the same thing for a sample, but I have different notation.
Is that the one with the x bar?
That's the one with the x bar, but where's x bar going to go in this formula?
At the top,
Where in the top? Here or here?
the first one?
Oh, so close. X bar is your mean, so it's always the mean minus, or your value minus the mean divided by the standard deviation, which in this case, sample standard deviation is S. Now here's what Google Sheets is doing for you. It's doing a lot. It used to be that we would calculate these areas by first of all doing a z transformation, and I'd have to calculate the z-scores, and that put things on the standard normal 1 curve, normal 0, 1 curve. So once I transform these values, then I try and find the area between those two, and then I'd have to look up those areas in a table, and then I have to write down those numbers and then subtract them. Wow. There's a lot of good reasons we're using Google Sheets. This was a royal pain, and now we don't have to worry about it. So that's really cool. Any other comments or questions on section 6.4? All right.